All right. Hello, I'm Abigail Flom. I'm from the University of Hawaii at Manoa. And as he said, I'm going to talk about water and hydroxyl behavior at lunar swirls such as Reiner gamma. So we're going to dive right in. So first I want to talk a little bit about lunar swirls themselves. These are bright albedo features on the surface of the moon that are not associated with topography, but they are associated with magnetic fields. But not every magnetic field has a swirl. So the idea is that these magnetic fields are protecting these locations on the moon from space weathering, and if it is deflecting solar wind protons, then for space weathering, then it's also potentially protecting it from hydrogen implantation, which would cause water and hydroxyl to be present on that surface as well. Oh, there we go. Okay, so there has been work done on lunar swirls in the past. These particular pictures are from Kramer et al. 2011, and they show a really distinct OH abundance deficit on the swirl, which you can see right here. However, not every analysis of moon mineralogy mapper data, which is where this is from, shows that same variation, and that's because of the thermal emission correction to moon mineralogy mapper data. So basically, if you don't correct for thermal emission, you'll get a spectrum kind of like this, which doesn't show an absorption feature near 3 microns, which indicates OH or water. However, if you model the thermal emission radiance, which gets started right in that area, then you can remove that and see the absorption feature. However, in moon mineralogy mapper data, there's a few different models for the thermal emission. And these different models are producing different results in terms of how the water band is varying across the surface of the moon and at lunar swirls. So we are using a telescope on Mauna Kea, the NASA Infrared Telescope Facility, and this telescope can go out to longer wavelengths, which are more thermally dominated, out to 4 microns, and is able to be used as an imaging spectrometer. So we can use this to look at swirls and see more of the thermal emission in order to try to get a better fit of that thermal emission and hopefully correct the data with more confidence. So I'm going to show you a few different observations today at 3 different phase angles. And so those include some special observations, such as times when we're in opposition and we're getting a greater proportion of reflected light to thermally emitted light, as well as during a local partial eclipse, which decreases the amount of solar reflected light, but also significantly decreases the temperature, which affects the thermal emission. It's also worth noting all of these observations were taken when the moon was in the Earth's magnetotail, so there was a lower solar wind flux at that time. All right, so I mentioned that one of our observations was during opposition, and basically when you're at low phase angles, so when the light source is behind you and you're here and your target is right in front of you, you're going to get a lot more reflected light, as shown on this part of the graph. And so during this time, at the same temperature, when the moon's in the same thermal equilibrium, we'll get a greater proportion of the reflected light than we would seeing it from other angles. So that's an advantage for us trying to look at the reflected spectrum specifically. And then we also have an observation during a partial eclipse. And so the main thing here is that the solar flux is being reduced. And so even though we are but it's also at this place of opposition. So even though we're getting less reflected light, we're getting as much of it as possible by being at this angle of getting the most reflected light possible. And, but we're also turning down the amount of light and turning down the temperature, basically, on the moon. So this table sort of sums up all of these observations. So we're scaling all of these to our observation at a phase angle of 18 degrees. So that's why here it's 18 degrees, and then our relative illumination and net received solar are at 1, because we're comparing all of these to that observation. And it's at a radiative temperature of 280 K. So then at our low phase angle observation, which is at 3 degrees, we're getting about 2.5 times the reflected light that we were getting at that other angle. And so then we're getting net about 2.5 times the reflected component. And that's at a radiative temperature of 330 K. However, when it goes into eclipse, we're still getting close to 2.5 times the reflected light, but we've reduced the solar illumination by about a third. So we're only getting about 70% of the light as we got for our mid-phase angle observation, but we've turned the temperature down to 240 K, which is pretty cool. All right, so this is just a quick look at some of our data. So this is a moon spectrum divided by a standard star. So that's removing the shape of the solar spectrum from the data. And we've also normalized this and stacked them. So basically, this lets us take a look at how that thermal component is varying relative to the reflected component. So you can see here, this is kind of a normal thermal component, and then at low phase angle, we had a higher thermal component, but then when we went into partial eclipse, it went way down compared to the others. And these two graphs show both an on-swirl example and an off-swirl example, since we'll be comparing the two. So then if you ratio those two off and on-swirl examples, you can compare between the on-swirl more immature material and the off-swirl more mature material. And one interesting thing is to look at the thermal contrast between the two. So if you see the slope here is now indicating how different the thermal signal is from the two different areas. So here we have a pretty, in these two we have a pretty high, but then once again in the partial eclipse, the thermal contrast has gone down, and that's because there's just not as much thermal signal there. All right, so before we get into how our data look thermally corrected, I want to take a moment and actually look at a higher latitude example of what the water feature looks like in our data, the water and hydroxyl 3 micron band feature. And that's because right here we have a atmospheric absorption band, so that's not being included. And that's right where this feature begins to dip down. But as you can see here, there's sort of a discontinuity, and you can see the band as it begins to come back up again over here. So when I'm talking about the band in our data, what I'm talking about is this discontinuity where you can see that it's gone down and is coming back up from a band after that absorption. All right, so basically, when we look at the MARIA as opposed to when we look at the Moon Mineralogy Mapper data, we do see a weak hydroxyl feature, so it's not as strong as seen in the Moon Mineralogy Mapper data, but it's still there. I realize that's a little hard to see, but what we did was we ratioed the off-swirl MARIA spectra to the on-swirl more immature spectra, and that helps us see the contrast better. So when you see a absorption feature here, that's stronger when the off-swirl spectra has a stronger feature, and that's weaker when the off-swirl spectra has a on par or less strong feature than the on-swirl material. So basically, this is showing us that it seems that the swirls do contain less hydroxyl than the surrounding maria, which is consistent with the previous results, though it's not showing as strong as a signal here. And this is just pushing it together, so it's a little easier to see, because I realize going across the band, it's hard to see the dip. And then we made a band ratio map, and we could see that there was a decrease in OH abundance associated with the location of the swirl in that as well. So in conclusion, we found that the water and hydroxyl band was stronger in the surrounding maria than it was on the swirl, which was consistent with those moon mineralogy mapper results that I showed you before, and that strengthens the conclusions of Kramer et al. 2011, and that feature was present even when we were in the magnetotail making observations. Can I answer any questions?
Any questions? Yes, it seems to be working. There is one here.
I'll ask the obvious question, and that is why is the hydroxyl different on swirl and off swirl?
So that was because they're located on these magnetic anomalies on the surface. So the idea is that the solar wind is interacting with the magnetic field there, and it's being deflected from this surface. And that's preventing both space weathering, which would cause that material to be darker, and that's why we think that there's that light, bright pattern there. But it would also prevent hydrogen implantation. And so the idea is that hydrogen's being implanted into the surface and interacting with oxygens on the surface to make water and hydroxyl.
Okay, so hydrogen implantation as opposed to removal of hydroxyl from minerals?
Yes, yes, okay.
Good.
Just a quick clarification, because you said it, but I think I missed it. In the
sure.
magnetotail,
Uh-huh.
you don't see any changes in the swirl. Do you see changes in the surrounding terrain?
So what I was saying was all of our observations are in the magnetotail, and simply
Okay.
that we expect
Oh.
less hydrogen implantation, so our signal might be weaker, whereas if we were outside of it, we might see more hydrogen implantation, and then we'd see a stronger OH signal in the maria or the swirl, depending on the flux of the hydrogen.
But you have data outside the magnetotail, right?
No. Oh, well, he does, I think.
Oh, okay, so you're just using a different
I'm using
selected
yeah,
data
I'm
set,
using
okay.
a telescope, and we don't have observations outside of the magnetotail
Now
right
I'm
now.
caught up, thank you.
Yeah.
Diana, quickly.
So was there any difference in the OH content during eclipse at the lower temperatures?
So not that I know of. We haven't really compared, we mostly compared off-swirl to on-swirl, but we haven't really gone between observations so far, just
That would be
because-
interesting to look at too.
Yeah, that would be good.
Okay, I think
Okay.
we should move on. Thank
Yep,
you very much.
Thank you.